So let's do example 4. I really want my pen back. What did I hit? Let's see. Oh, well, I guess I'm not getting it back. Okay, so why don't you guys try example 4, and then I'm going to work on trying to get my pen to come back while you guys work on that. Okay, so I failed at getting the pen to come back. Oh no, something else is happening. Now I'm writing with a little spinny circle. Oh well. All right, so I started the ratio test and realized I forgot to hit record, but everywhere I saw an n, I plugged in an n plus 1, multiplied by the reciprocal of the original because I'm dividing. So this is going to be equal to the limit because n goes to infinity. So I'm definitely not going to have enough room here. I'm going to try to write really small. So that's n times x plus 2 times 3 to the n times 3. Oh, look at that. I did get it in there. Okay, so then this is 3 to the n. Actually, I could have split this up differently, but that's fine. So 3 to the n times 3 squared times n times x plus 2 to the n. Oh, now this thing is back. Okay. And then I'm going to see what cancels. So the x plus 2 to the n cancels with this. 3 to the n with this 3 with one of those 3's. And I think that's it. So that's the limit as n goes to infinity of x plus 2 is the coefficient of the n plus 1 over just n, it looks like. 3n, sorry, I forgot about this 3 right here. Okay, so then I'm going to compute this limit. I'll do a different color. So that limit is going to be just the absolute value of x plus 2 over 3. All right, because the n's had the same degree. Okay. And even if I had multiplied all of this out, the x would be a coefficient of the n, the 2 would be the coefficient of the n. I could factor the n out, I have the x plus 2, and then the x plus 2 times 1 isn't going to be attached to the n, so it's not part of the coefficient of the highest degree term in the numerator. So this converges when it's less than 1, so that means that negative 1 is less than x plus 2 over 3, which is less than 1. I'm going to multiply both sides by 3. Negative 3 less than x plus 2 less than 3. Subtract 2. Negative 5 less than x less than 1. All right, hopefully I didn't mess that up anywhere. So that's my interior of the interval of convergence. Looking at this, the very center, the thing in between negative 5 and 1 is negative 2. Well, if I look back up here, this is centered at negative 2, x minus a, x minus negative 2. Also, the radius of convergence is going to be the distance from the center to an endpoint, or you can just take the total distance, which is 6, divided by 2, you get 3. Right? Either way, same thing. Okay? All right, so then we have to check the endpoints. So I'm going to, again, make room, because there's no way I was going to squeeze it all in here. Are you going to work? Kind of. Okay. So how about, so I don't take up all this video time just talking through me writing, you guys test the endpoints, use the convergence tests, pause the video, and then hit play when you're done, and I'll have the answers written up. Okay, so I wrote one of the endpoints up right now because I was running out of room and I wanted you to see it. So I plugged in negative 3, I did some algebra, I broke apart the negative 3 to the n as negative 1 to the n times 3 to the n. It's the same thing. That way I could cancel some stuff out. and then I saw that I was left with an alternating series, but the a sub n is actually increasing. Right, so the limit's not zero, so either one of these I think would have been sufficient to show it diverges. But you have a series that's alternating, and the a sub n is getting bigger, so the magnitude of each term is bigger, so this thing is going to be bouncing, you know, over here, then way over here, then over here, then over here, then over here, so it's going to diverge. Okay? All right, so pause it again. I'm going to erase this, so make sure you get what you need. I guess you could just rewind it. And I'm going to write up the other endpoint, but notice this was divergent, so -5 is excluded from the interval of convergence, right? Okay, so plugged in 1, found out that it's actually divergent when x is 1 as well. So the final answer for the interval of convergence is what I have in blue right here, okay? But just make sure you have to actually prove at each endpoint by using, maybe it'll end up being easy, like it's just the harmonic, but worst case scenario, you have to actually use one of the convergence tests on it. Okay? All right, so this last piece here at the bottom, this is really kind of goes with the next day's lesson, but just to get you thinking about it, sometimes we can write a rational function as a geometric series or as a power series. In this case, it's a geometric power series in a way because the common ratio is just x each time. So if you notice, that's what it kind of says right here. You want to memorize this, but you should already know it because you know that a sub 1 over 1 minus the common ratio is the sum of a geometric series where the ratio is r. So that'd be a1 plus a1 times r plus a1 times r squared, a1 r cubed, and so on, right? So usually we start with this and we end up with this, well, we can just work in reverse. Same thing for a power series, except in this case, the common ratio is x. So just to get each term, I multiplied by x. First term was 1, common ratio is x. I could come up with this, write it in series notation. That works, and what do you know? We started at 0 again. Okay, so if you wanted, you could do the ratio test and find out that this is valid from -1 to 1. But we really shouldn't have to do that because we know that a geometric series converges when the absolute value of the common ratio, well, in this case, the absolute value of x is less than 1. Well, that happens when x is in between 1 and -1. Right? So that's a little bit different. If we did the ratio test, we would end up with this, and then you would test the endpoints to find out they're excluded. But since we know this is coming from a geometric series, we don't actually have to test the endpoints on this. Okay? So this is just a recap at the bottom of this page, just to make sure you're good with everything up until this point, because the next unit, or sorry, the next lesson, we're going to be basically going off the assumption you have all this stuff memorized now. Okay? So just to recap, if we write a function as a power series centered at x equals a, we call it a Taylor series with a center at x equals a. If the center is 0, we just usually call it a Maclaurin series, but you could also call it a Taylor series centered at 0. And you have to know both. As you increase the degree of a Taylor polynomial, the approximation of the function becomes more accurate. So basically, the more terms you use, the higher the degree of the polynomial, usually the better your polynomial is at approximating the function. Finding the Taylor series has two problems that we've already talked about, but usually they only converge for certain values of x. That's why we need to know the radius and interval of convergence. It's not obvious just by looking at it. You have to find these things. Also, there are functions that are not equal to the sum of their Taylor series, but the nice thing is you don't have to worry about it in this class. So imagine that last sentence isn't even on the paper. Okay? If you have any questions, as always, email your teacher. Come find us.